Hello students, your physics teacher Hassan Darwish with you. Now I continue in this video the explanation of chapter 4, Mechanical Oscillations. And in this video I am going to explain the real oscillations of a pendulum, which I call here experimental study. Now you know in reality, in the real world oscillation, dissipative forces do exist, right? And oscillations die out with time, as we see in the following experiment. Let's do this experiment. Let's first here start from the beginning. Now in this experiment, what we have here? We have in reality horizontal elastic pendulum. But in this experiment can be applied to any other pendulum, torsion or compound or simple. Clear? For simplicity, I've chosen the horizontal elastic pendulum, in which here is the elastic spring and this is the block. Clear? And as you see here, dissipative force, which is friction force, in reality does exist. Okay? This is called restoring force or the elastic force. Clear? Elastic force of the spring or tension of the spring. Now here we pull the block to the right, so the restoring force is to the left. Now because the spring here is pulled to the right, means the elongated and the block is still at rest, the total energy in this system is only elastic, which exists in the spring. Look here, only elastic potential energy. We choose this as a reference for GPE, so we can say GPE 0. Let's see the experiment. Now, as the body oscillates around its equilibrium position, look what happened to the amplitude of oscillation. The amplitude, as you see, decreases. Also, the two forces here, the weight and the normal reaction, are constant forces. While look at the restoring or elastic force of the spring and the friction, they are variable forces. At least they change direction. Clear? But in reality, the magnitude and the direction of the two forces are variable. Okay? So, here is our horizontal elastic pendulum. I've chosen K equal 1 Newton per meter and mass of the block 100 grams. So I can find the proper period. You know how to calculate the proper period of oscillation. You remember in the first pendulum, we calculated T0 for the elastic pendulum. We proved this as 2 pi square root m over k. Now if you replace, you get the number almost 1.98 seconds. Okay, here is our elastic pendulum, and this is a ruler to measure the amplitude. And we have a clock to measure the time for each oscillation. Okay? For each oscillation, means back and forth motion, I measure the period or the time. Then let's draw the graph. This is the amplitude, xm, amplitude of oscillation, xm. And this is the time. Clear? Now, this motion, the back and forth, in reality represent one cycle, one oscillation. This is the second oscillation. This is the third oscillation, fourth oscillation, etc. Okay? Okay. So let's see what we observe from the graph here. Now observation. What happened to the amplitude of oscillation? Decreases with time. The amplitude is not constant as in the case of undamped. Why? Due to dissipative force, maybe friction. So what do we call this type of motion? Damped oscillations. Okay, so the mode or the type of oscillation is damped oscillation. Some people call it damped simple harmonic motion. But look also, the time taken to complete one oscillation or one cycle is constant. This is very, very, very important. Okay, so this is constant. Let's look at the graph. The time for one oscillation, this is the first oscillation, here to here. In reality, 2 seconds, right? 2 seconds. Also, from here to here, maximum to maximum, also 2 to 4 means 2 seconds. Also here to here, 2 seconds. 2 seconds. So the time for one oscillation is only 2 seconds, or is constant. This means what? It seems for us the motion is periodic. Why? Because motion repeats itself every constant interval of time. But in fact, it's not periodic motion. Why? The motion seems periodic, as I said, but in fact it's not. It is pseudo-periodic, means it is counterfeit, not true periodic. It is pseudo-periodic. Why is this? Since it is not repeated identically. Why it's not repeated identically? Because the amplitude decreases, and reality the wave does not, or the cycle is not repeated identically as in the previous cycle, since the amplitude is smaller. That's why motion is pseudo-periodic, and the pseudo-period is t. T is always bigger than t0. Why? Because we measured here the pseudo-period 2 seconds, and before we have calculated the proper period or natural period 1.98. Clear? So if t bigger than t0, of course, f smaller than f0, because f is 1 over t. Now you may say, what's the difference between t and t0? t0 is called theoretical period, means natural period, means the period of oscillations when we neglected all types of friction, where the mechanical energy of the pendulum is conserved, while t, the pseudo period, is the period of oscillation in the presence of friction. Clear? That's the difference. Okay, let's continue. Experimentally, we observe that as the damping force or damping increases, the pseudo period also increases. So be careful. T0 fixed, constant. Clear? Here we neglected all types of friction. What T0? Function of friction or dissipative force. Function of friction depends. As friction increases, pseudo period increases. Okay? Any problem? Now, I have this important remark. Usually, I give it only for GS students. It doesn't mean it's not required for LS, but usually we give it for general science students. Now, what is this remark? In damped oscillations, the damping force is, non-conservative force. Why we call it non-conservative? Because it makes the mechanical energy not conserved. So the mechanical energy of the system is not constant, but decreases with time, continuously, and eventually becomes zero. We know this from chapter 1. In the presence of dissipative forces, the mechanical energy decreases and it changes into heat. Remember? And we remember this rule. Delta mechanical energy is equal the work done by the dissipative forces, non-conservative forces. So let's suppose that the friction is minus bt, or you can take it in the vector form. B is a constant. Let's find the power of the friction force. Newton's second law here, sum of forces, is equal ma, right? I will apply it to the horizontal elastic pendulum in our experiment. So it means that weight plus normal plus friction plus this tension in the spring, which is a restoring force, is equal ma. Now because x prime x is our reference frame, so minus friction, this is the magnitude, minus tension, also this is the norm of the vector, is equal to ma. It means what? Minus bv minus kx equals ma. And you know that in rectilinear motion, a equal v prime equal x double prime. So you can obtain the differential equation if you like, mx double prime plus b x prime or v plus kx equal to 0. This is the second order differential equation for the damped oscillation. Let me now find the mechanical energy. Mechanical energy at any time is half mv squared plus half kx squared, right? Here we suppose GPE equal to 0 since the body moves on the reference. Now let's make the derivative. Derivative me prime is equal, I cannot say it is 0 because it is not constant, be careful, over dt equal v prime plus kx x prime, right? Now let's rearrange it. We get, let's take here as a common v, okay? So we get, v into mx double prime plus kx. Now replace this equation. Look at this equation, mx double prime plus kx equal minus bx prime or minus v. So we can get this is equal v into minus bx prime or v, right? You can write it in this form, minus bv squared. What is this? This is minus bv vector dot v vector. So what is this? This is friction or non-dissipative force dot v. But this is the power of F. Power of this dissipative force. Hence, the power of the dissipative force or the friction force here is minus F dot, not minus, it's F because the force itself is negative. Is F dot V, where V represents the instantaneous velocity and F is the dissipative force, equal derivative me prime. Let me write it me prime since you like it more. Me prime, where me prime represents the derivative of the mechanical energy with respect to time. Okay? And this is the instantaneous. Remember this, you can say it is the derivative of the work of the force also. This is everything in the chapter. Okay? Study it well and take care. Bye-bye.